Let's start by understanding how React's reconciliation process works in functional components. Here's a simple example. A functional component that increments a counter. Notice how we use useState to manage the component's state. Every time we click the increment button, setCounter updates the state, causing the component to re-render. This is where React's reconciliation comes into play, comparing the previous and new states, and updating the DOM efficiently. Keep an eye on how the counter updates with each click. In this example, we're focusing on how state changes trigger React's reconciliation. We have a functional component, nameDisplay, with a piece of state name, initially set to John. Using useEffect, we're simulating a delayed state update, where after 3 seconds, the name changes to Jane. When the name state changes, React's reconciliation process kicks in. It compares the previous and new render outputs and updates the DOM where necessary. Watch how the displayed name changes from John to Jane, showcasing the re-render process. Now, let's focus on rendering lists in React and the importance of keys. Here we have a list example component rendering a list of fruits. Each fruit in the array is rendered as a list item. Notice how we're using the array index as the key for each list item. While this works, it's not recommended for dynamic lists where items can change positions, as it can lead to inefficient and buggy updates. Keys should be unique and stable identifiers, like IDs from a database. Here's an interesting aspect of React's reconciliation process. We have a toggle component that switches between rendering a paragraph and a heading. This toggle is managed by a state variable, isParagraph. When you click the button, the state changes, and React will completely replace the paragraph with a heading or vice versa. This happens because they are different types of elements. React doesn't just update the text. It removes the old element and inserts the new one, showing how component types impact reconciliation. In this counter component, we're dealing with a common performance pitfall: inline function declarations. Notice how we use the useCallback hook for our increment and decrement functions. Without useCallback, these functions would be recreated on every render, potentially leading to unnecessary re-renders of child components. By using useCallback, we memoize these functions based on the count state, ensuring they are only recreated when count changes. This practice is crucial in larger applications where performance optimization is key, especially when passing functions down as props to child components. Have you ever wondered how to prevent unnecessary re-renders in React? This is where React.memo comes in handy. In this example, my component is wrapped with React.memo, which is a higher order component. It tells React to memoize the component, meaning it only re-renders if its props change. Here, my component receives a static text prop. Thanks to React.memo, despite the parent component re-rendering, my component will not re-render unnecessarily. This is particularly useful for optimizing performance in components that receive complex or unchanged props. In this example, we're delving into useEffect and its impact on reconciliation. Our user status component initially shows the user as online. We then use useEffect to change the status to away after 5 seconds. Notice how useEffect is tied to the component's lifecycle. The empty dependency array means the effect runs once after the initial render. We also provide a cleanup function to clear the timer, an essential practice to prevent memory leaks. This demonstrates how useEffect interacts with the render cycle, allowing side effects while keeping them in sync with the DOM updates. Let's explore how conditional rendering affects React's reconciliation. In our conditional rendering component, we use a state variable, showMessage, to control whether a message is displayed. Clicking the button toggles showMessage, and based on its value, the paragraph element is either rendered or not. This is a great example of how React's reconciliation efficiently updates the DOM. When showMessage changes, React compares the virtual DOM with the actual DOM and updates only what's necessary, either adding or removing the paragraph element dynamically. In this immutable state component, we're demonstrating the use of immutable data structures in state management. When we add a new item, notice how we're not modifying the original items array directly. Instead, we create a new array with the spread operator, adding the new item at the end. This approach maintains immutability, which is vital for React's reconciliation process to efficiently identify changes in the state. By avoiding direct mutations, we help React in making smart DOM updates, enhancing performance. In our profiled component, we're using the React profiler to measure performance. The component has a count state that increments every second. Wrapped inside a profiler tag, it logs performance information on every render. The onRender callback function provides insights like the render duration and phase of the lifecycle. This is a powerful tool for identifying performance bottlenecks in your application. By analyzing this data, you can understand how often and why your components re-render, guiding you in optimizing their performance for a smoother user experience.